starting a new chapter, complete a new chapter, let's say. This is passive filters, not the active ones, but the passive filters. This is a huge subject, of course, so we will be dealing with a small part of it, which is passive filters only. And we will be doing the analysis plus the synthesis in this subject. So the first thing that we're going to examine is transfer function. Transfer function, it is a critical function because it determines the filter characteristic of any circuit directly. And then we will be examining filter classification. After that classification, each group will be examined in details: low pass filters, high pass filters, band pass filters, and band reject filters. Let's go into passive filters. So the first thing, the definition of the transfer function, and then we're going to compare transfer function with the Thevenin equivalent circuit, how to use these two subjects in order to analyze one of the elements current and voltage within a circuit. So we're going to compare those two, and then we will be examining transfer function, how to use the transfer function in the analysis. In here we will see the relation between sinusoidal steady state solution and the transfer function. And lastly, this is going to be a separate video, of course, but this is related with the gain, new quantity that which is commonly used in electronics. So that's going to be a separate video. Let's go in details now. We've got to move to open board. So move that in. So transfer function. So each circuit has got an input and an output. If this circuit is a linear circuit and if there is no energy stored within the circuit, what it means, all the capacitors and inductors has no initial conditions in it. So we are mentioning about this initial conditions, no initial conditions at all. We know that initial condition, if there is an initial condition, let's say for a capacitor, the stored energy for this capacitor will be 1 over 2 C VC initial condition square of it, isn't it? That's the energy stored. So we are saying there is no energies like that in capacitors, and there is no energy stored in the inductors. Under this condition, if you divide the output function Laplace transform to the input function Laplace transform, the output function as seen here is Ys, the input transfer function is Xs. So the ratio of those two gives that transfer function. That is the transfer function. So that's the definition. Once you know the definition, once you calculate this transfer function, then we can find out the output in terms of input, isn't it? So multiplication of those two gives you the output. So you could use that transfer function in the calculation of the output function. once the input is given. For the analysis, input must be given, the circuit must be given. When the circuit is given, I can calculate the transfer function. Once I calculate the transfer function, I can calculate the output function. So some of the properties of the transfer functions is listed here. That transfer function is defined for linear circuits. So the circuit should be linear. It is not written here. Let me write it. Linear circuit. That means no nonlinear element included in this circuit. If there are nonlinear elements, not easy to define the transfer function. Input could only be an independent source. So it's going to be one independent source here. If there are more than one independent sources included, then transfer function wouldn't be only one function, so it is a bit difficult. So consider that input function is just one function, a one independent source function. Output could be the voltage or current of any element within the circuit. We can define the output as an output of an element voltage or current, so that means Ys could be Vs or Is. Input voltage source, output voltage of an element could be example given here. Output solution found by transfer function is force solution. So the output function, if you transfer this output function here from S domain to time domain, the solution that we found is a force solution. Why is that? Because we defined the transfer function when the initial conditions are zero. If the initial conditions are zero and the only energy source is the independent source, then the solution that we are going to find is going to be force solution. That's the definition, so it fits in. Transfer function does not change by input sources. So you see here, that is input function and that's the output function. So if you write the output, these two is going to disappear. So transfer function is independent from the input. So in linear circuit it is true, isn't it? We were saying in linear circuit the output of a voltage or current is, when you found the solution, that means your solution is going to be like that. So that means you're going to write the output element voltage in terms of source function, isn't it? Source function determines all the outputs, critical. So if you try to find out the transfer function, you're going to move that Vs. So in here, Vs not included. That is transfer function. So what is said here is true. By using the transfer function, output function could be calculated for different inputs. So, but this is by definition you could do that, isn't it? So if you change the x, so that is the how we write the output function in terms of transfer function. Now we are saying if we change the input function or independent source function, we are going to get the output for that input. If you change the input to another function, so you're going to find the output for this new input. So for different inputs, I can write the output function by using this transfer function. So the next step, now in here, the last thing we are saying is this. By using transfer function, I can find one of the element voltage and current. This element is the output element. So what I said here, this transfer function helps us to find out one of the element current and voltage. But on the other hand, if you remember, there was another subject that we use for analyzing an element current and voltage. The subject that we use in the calculation of one of the elements current and voltage was Thevenin and Norton equivalent circuit. If you remember, if you got a circuit, linear circuit, and if you are dealing with only one of the element of this circuit, let's call this element as load. Now we said what we do, first we get the Thevenin equivalent of this circuit, including the source. So let me write this source as well here. So equivalent of this circuit, Thevenin equivalent of this circuit will be a Thevenin independent voltage source and Thevenin impedance ZTH. So that is equivalent of this. These red ones equivalent to each other. And then we said if we connect to the terminals A and B here, they are equivalent. If you connect this load here between the terminals A and B, Z load, we said this load current is equal VTH over ZTH plus ZL, isn't it? So by using Thevenin equivalent, I found out one of the element current and voltage of a circuit. But this element, the Thevenin equivalent that I found here, is the circuit Thevenin equivalent except the ZL load, isn't it? So this ZL element, although at the beginning is within the circuit, so I put this out and find out the equivalent of rest of the circuit as Thevenin equivalent circuit. By using this Thevenin equivalent circuit, I can calculate the current and voltage, the element that I have chosen as a load or as an output element. Now when you come to the transfer function, so you are not moving this element out, you are keeping this element inside the circuit, keeping the output input at the output. So ZL now is in here. And we are saying that if this is the output and if this is the input, output over input gives you the transfer function. Once you do the transfer function, by multiplying the transfer function with this independent source, you can find the output. So that's the difference between Thevenin equivalent and the Thevenin transfer function for the calculation of one of the elements within a circuit, isn't it? So we kept that load at the output of the circuit. In here, we kept that load within the circuit. While this load inside the circuit, I transferred it, defined the transfer function and find this transfer function and then did the analysis. So what are the other differences between those two? Do not include the output element, Thevenin Norton, do not include the output element. And transfer function does include the output element, does include the output element. Represent this circuit except the loads. So Thevenin equivalent, represent the circuit except the load. So that's the one. Represent input-out relation of a circuit. In here, HS transfer function represent the relation between output and the input, isn't it? and do not change when the load changes. When you change the load, here, so put another load here, this equivalent circuit do not change. That is as it is, isn't it? Because I kept this outside the circuit. So therefore, when you change the load, equivalent circuit, Thevenin equivalent circuit does not change. In here, does change when the output is changed. When you change the load element, then your transfer function changes. So different, isn't it? Do not change when the load changes. Do change in here. Do change when the source change. If you change the source here, of course this Thevenin equivalent circuit is going to change, because this calculation of this is going to be calculated when another source in here. But in this case, transfer function do not depend on the sources, and the sources here. So these are the comparison of those two. So okay, we examined to find out one of the element, current and voltage, by using the Thevenin equivalent circuit already. Now let's examine this now, how we could use the transfer function for the analysis of an element within a circuit. These are some of the examples that we can see here. Consider this circuit. So if the output is the output of this capacitor voltage, so I can define a transfer function here. How I'm going to do it, these elements are connected in serial, so the equivalent impedance is going to be R plus SL plus 1 over SC. That is the equivalent impedance. So if I divide the VG to this impedance, R plus SL plus 1 over SC, I'm going to find this current here. So this current is equal to this. So if I since these elements are connected in serial, this current also is the current of the capacitor. If I multiply the capacitor current by its impedance, which is 1 over SC, I'm going to get the V output value. So, and then if you move this to here, it becomes transfer function. So that is the transfer function. Which is this. So what we are saying is this: any independent source connected to here, the Laplace transform of this function is going to be multiplied with this transfer function. When you multiply it with this transfer function, you're going to get the output function. So output function in S domain, transfer it to the time domain, so you found the solution for this given input. So we did the analysis. So in here, I have done one of the elements, so this element here, voltage. Not all of the element voltages, all element the currents. So this is another example here. This 2 is connected in serial. 2 plus SL is the equivalent of this. And this one is in parallel with this impedance. So if I say this impedance is, let's say, 1 over SC, C is 0.1 S. So if you find this, that's going to be this circuit equivalent of this circuit, isn't it? Z equivalent. So if you multiply Z equivalent with this current input, it's going to be equal to the voltage of this impedance, isn't it? Voltage of this impedance is also the voltage of this capacitor, so that means VR. So if you move this one to here, that becomes transfer function. So by using the transfer function, when the input is given to you, any source, it could be a DC source. If it is a DC source, let's say 5 volt, so transfer function of this is 1 over S, isn't it? So if it is a sinusoidal function, let's say 5 cos 10t, so Laplace transform of this is 5s over s squared plus omega squared, which is 100. So if you multiply this transfer function with this one, you get this VO for this input. If you multiply this transfer function with this input, so you can get that V0 for this DC source, V0 output for DC source. So I calculated one of the element, current or voltage of an element within a circuit by using the transfer function. So that's another example similar to this one, but a dependent source. The source changes, and the source from the independent current source, it became an independent voltage source. So in here, independent voltage source voltage is here. So this is ramp function, isn't it? Ramp function. So it is a function like that. So you could use it for a short while. If you continue, keep that independent source on the circuit, it's going to burn, isn't it? When T increases, the voltage increases. If it is increases after a limit, so your circuit burns. But if you run it for a short time, so still you could see a solution in your circuit. So transfer function is given here. So you could calculate this transfer function. What you're going to do, you're going to find V0 in terms of Vg. If you do so, that's going to be transfer function. Once you found the transfer function, so for this input now, transfer function of this input, Laplace of this input is given here. So if you multiply the transfer function has been calculated here, so which is this. Multiplied with the input, you get the output. So this is a rational function, so you're going to transfer this rational function to time domain. When you do that transfer, you're going to end up with this, isn't it? So if I move this a bit up, so this is the solution here. So if you look at that solution, since the characteristic roots are complex roots, then this part comes in. Why that came? Okay. This part here is homogeneous part. That part is particular part. Why I said so? Because this comes from the circuit, this comes from the input, isn't it? This is input type of function. You see that function? So input type of function. Since it is input type function, it is a particular solution. This solution we found here is a force solution. We already said that by using the transfer function, the solution that you're going to find is the force solution. Why is that? Because the initial conditions are zero. In here, initial condition has been considered as zero. In the definition of the transfer function, we also said that initial conditions are zero. No energy storage included in the circuit. So that is the explanation of how to use the transfer function in the analysis of one of the elements within a circuit. Now the next thing that we are going to examine, the relationship between the sinusoidal stated solution and the transfer function. That's going to be very critical, so we've got to understand that. So now what we are saying, we are limiting ourselves now. We are saying assume that input is a sinusoidal input. So question is, if I find the transfer function of this circuit, which is Hs, what would be the output? So the first thing to do is find the transfer function, find the Laplace transform of the input function. Laplace transform of the input function is this. So I just remind you how we calculated that. So since this is cos omega t plus phi, so you can consider that one as alpha and that as beta. There is a trigonometric relation that we already know, cos alpha plus beta is equal cos alpha cos beta minus sin alpha sin beta. So if we do so, here you are, cos omega t cos phi minus sin omega t sin phi. Since there is a coefficient a here, those two terms are multiplied with a. So on the other hand, we know that Laplace transform of this function is s over s square omega square, and Laplace transform of this term here is omega over s square omega square. So if you replace all those two, you're going to end up with this. So that is the Laplace transform of this input. So if I multiply the input Laplace transform with the transfer function, I get the output. So that is the output in S domain. The next thing that we're going to do is find out T domain corresponding to that function. Two domain function corresponding to this S domain function here. But we said we are going to calculate the output, but not the whole output. What I mean by saying whole output, we said we are going to calculate only the particular solution. Particular solution. Why is that? If you remember, the homogeneous part of this solution is going to disappear after a while, as we did it in the frequency domain. So since it is going to disappear, I am not going to deal with the homogeneous solution, but the particular solution. Now I would like to find the particular solution part of this ys function. So how am I going to do it? So normally, if there is a rational function in S domain, to find out the inverse Laplace form of this function, you've got to find the characteristic roots. Characteristic roots are the ones coming from the denominator of this Hs function. So it is included here. And the other two comes from that independent source. So for these roots, I'm going to calculate these residues or these coefficients. Since I am dealing with only the particular solution, which is, since the input is the sinusoidal function, so it's going to be sinusoidal steady solution. That solution we are dealing with, which is the same as this. We will be calculating this part of the solution, not this part of the solution. Why is that? This part of the solution is related with the homogeneous solution. Why is that? Because this is related with the circuit, isn't it? Not the inputs, the circuit. The solution comes from the circuit is the homogeneous solutions. If you remember the homogeneous solution, you are deactivating all the energy sources. So that means no sources included. So no sources included. These are the source part of it. In here there is no source at all. So therefore the solution that you found by this part is the homogeneous solution, and this part is the particular solution. So what I am going to do, find out this K. How we are going to find this K? So let's do it now. Rule was this: you're going to multiply left hand side and right hand side. So we said we're going to remove that. And let's clear this area. So I need this area to write. The rule is this: we are going to multiply left hand side and right hand side with S minus j omega and replace S equal j omega. This is what I am going to do on the right hand side. I will be repeating the same thing on the left hand side. That means multiplied with S minus j omega and replace S with j omega. So if you remember, if you do so, since you multiplied all these terms, that means fractional terms here, if you multiplied it with this one and then replace S with this one, so all these terms are going to be 0, isn't it? So you are multiplying it with S minus j omega and replacing S with j omega, it's going to be 0. So all these terms are going to be 0 on the right hand side. So for this case, also it's going to be 0, isn't it? You are multiplying this with S minus j omega and replace S with j omega, so this is going to disappear as well. So if you do this multiplication for the first time, this S minus j omega, this S minus j omega, so disappeared. What is left on the right hand side is just K1. So I am trying to find out, calculate this K1. So K1 we found on the right hand side of this equation. What we have on the left hand side, so we are going to multiply now this ys function with this S minus j omega and replace S with j omega. Now this can be written now as the multiplication of those two, isn't it? S minus j omega, S plus j omega. So let me clear this. So I can explain it. So that is S square omega square. So roots of this equation is equal to 0. Root is S square is minus omega square. So S is minus 1 omega, so plus minus. That is J, isn't it? So S is plus minus J omega. So the root of this second order equation is plus minus J omega. So for these roots, I wrote the function here. So if we do this operation now, so this Sj omega, this Sj omega is going to disappear, and I am going to see S with J omega anywhere I see here. So let me move it here. Now A S cos phi minus omega sin phi over Sj omega, and this Sj omega disappeared. What is left underneath is just S plus J omega. And I have got it Hs at the beginning here. So I am going to replace S with J omega. This is what I am doing here. Multiplication, so those two disappears. What is left written here? In here, I am going to replace S with J omega. So if we do so, this is going to be end up with Hs, H, J omega, A, there's an S here, J omega, minus omega, oh sorry, that's cos phi, I have forgotten. Let me write it. J omega, I put for this S, so it's going to be cos phi minus omega sin phi over, if you put S with J omega underneath, I'm going to end up with 2J omega. So what is this? H J omega. H J omega cos phi over 2J omega minus omega sin phi over 2J omega. So if I move that 2 and 2, and A is also common in both of them, isn't it? That A is common both. So it is like that. And this is, if I put A over to here and move that, so that's the multiplication. So J omega disappeared. This omega disappeared. If we move that J upwards here, it's going to minus 1. So it's going to be here, A over 2 H J omega cos phi plus J sin phi. So if I write now this one, so this is equal to K1. So I'm going to write this K1 in a different way. K1 A over 2. So this is a complex number, isn't it? I can represent this complex number in polar form. It's going to be H C omega module e to the power, let's say the angle of this is phi. So that's the angle of this. Angle of H J omega is phi. So it's going to be J phi. So that is the polar form of this. So what is this? According to earlier formula, it is e to the power J phi, isn't it? So e to the power J PC, that's PC, that's phi. So if this end up with A over 2 8J omega module e to the power J phi plus PC plus P. That's K1. So how I am going to transfer that information to time domain? So we said we are dealing with, let me clear this area once more. We said we are dealing with only this part particular solution, not this part. So what is this part corresponding to time domain? So we know from the list that if there is a fractions like those in S domain, the corresponding time domain function is this. So look at this. In here you've got k is that k, and this angle here is the k angle. So theta is this total, isn't it? This is k. So that theta here, let me use a different color. So that theta here is this. K module is the module here, so it is this, isn't it? K module. That's K module. And what is left, this beta here, is omega, isn't it? S minus j omega it was, isn't it? So that beta here is omega here. What is this omega? This omega is the input function, input sinusoidal function frequency, isn't it? So if I write now the output, it's going to be t times, that was k module multiplied a over 2 8 h j omega module, and then cos beta was omega, so omega t plus theta. Theta is this, so phi plus pc. So let me write, so this is a bit, okay, nice. So that's the conclusion. So that is yt, that is particular solution, that is sinusoidal steady solution. So this goes. What we end up with is this here. So how we are going to interpret that result that we found here is easy. You see, let me move that up here. So that's the input, that's the output. How you can write the input by just looking at the input is quite easy, isn't it? Let me show it in different columns here. So if I multiply that A with G, with this, that's the transfer function, isn't it? Transfer function S is replaced with j omega. The module of it is going to be multiplied your input function. That's the input function. And that part is also input function. Here you are, omega t and phi. And you're going to add that theta here. That theta is phi, isn't it? So you're going to apply the theta. So this is in your input function angle. So you're going to add a new angle here. That new angle is the transfer function angle, isn't it? That's theta here is 8j omega angle. So in here, my theta, when I say theta, is this theta, you see. When you put theta, so they wrote it separately here, but you're going to add your transfer function angle. So conclusion is quite easy. If you know the transfer function, you can write the output function directly on the input function. All you got to do, module of your transfer function is multiplied your input function, and your transfer function angle is going to be added to the angle of the input. So that is a strong solution that we found here, saying that if you know the transfer function, you can directly write a particular solution. And then we can say that that solution tells us the characteristic of the filter characteristic of our circuit. So in terms of filter characteristic, transfer function is very important. How it is important, let me explain it. So we are saying now, that's the input and that's the output. If Hj omega is equal to 0, what it means, my output is equal to 0, isn't it? If 8j omega c is equal to 1, my output is like the input, isn't it? So it's going to be a cosine omega t plus phi and theta. So if you add an angle to that angle, that means you are shifting the sinusoidal function to left and right. It's not that much cosine, just a shifting operation. So interpretation of this conclusion tells me that, assume that Hj omega, let me clear area here. Now let's say you have Hj, Hj omega module and omega here. If you got a characteristic like that, what this tells here, that explanation, in here, let's make it different. Hj omega module is equal to 0. That means at the output is 0. If the omega is bigger than omega c, then I am not going to see anything at the output. If omega jc is equal to what, which is this area here, I'll make it blue. That means when the omega is less than omega c, then your transfer function module is equal to 1, then you're going to see that output. That output is going to be the same format of your input, isn't it? So that means this sinusoidal function, of which frequency is in between these two frequencies, are going to be observed at the output, while the other frequency sinusoidal functions are not going to be seen. That means you made a filter, isn't it? So this is a pass band, which is called low pass filter. Why it is low pass filter? Because low frequencies can be observed at the output here, but high frequencies, which is higher than omega c, cannot be observed at the output. So that means you filter out these frequencies. All these frequencies disappears at the output. Only these frequency signals are going to be observed at the output. That is directly related to the filter characteristic. That's why we said the transfer function is very important. Similarly, let me clear this area as well. So this transfer function angle is going to added here, transfer function angle. If I draw the transfer function angle as well, if this angle is constant somewhere here, then it's good to be news, isn't it? This angle is called group delay. Delay, if there is a delay for different frequencies, different delays, so you confuse the signal that you're going to get. Your feeling is going to be not a proper feeling, because the different delays in different frequencies changes your understanding of the signal. Let's say this signal is transferred to a voice, so this voice is going to be a problematic voice. So the change of angle of 8j omega c is critical as well in terms of group delay. So we end up with the characteristic of a filter depends on directly to that transfer function changes with respect to omega. That's why transfer function is important. For this one we will be having a new video, so let's stop this video here.